Well, now that you have played around with that applet and you've come up with a conjecture about what the derivative of a polynomial of degree n should be, let's see if you're right. So we're going to come up with a big derivative rule here called the power rule. We've got a power function x to the m. We want to take its derivative. When in doubt, what do? We go back to the limit definition. If this is our function f of x, then f of x plus h is x plus h to the m, and f of x is x to the m. So when we did this for quadratics, and I think on your homework you had a cubic, what you next did was you multiplied this all out. So what does this mean? This means I'm taking x plus h times itself m times, and then minus an x to the m at the very end. So if you multiply all these terms together, the natural first term that everybody always writes when they do this is x to the m. And one way to think about how you got that x to the m is that in each of these terms you had the choice of either choosing the x or the h to multiply. And x to the m represents doing what? It represents choosing the x every time. So that you chose x from here, x from here, x from all of those, and x from the last one. There were m of those along the way. So there are m times here. And so you just get x times itself, m times. Then the traditional way to write the next term is some number of, is one fewer x's. So x to the m minus 1, and then h to the first power, which we just write as h. So one way to think about how that happens is that you chose the x every time except one. So you chose m minus 1 x's and 1 h. So let's count how many ways there are to do that. You could choose the h from the first term, and then x is all the rest of the way. You could choose the h from the second term, and x from the first term, and x is all the rest of the way. You could choose the h from the third term or the fourth term, etc., or you could choose the h from the very last mth term. So what that means is that there are m ways to choose exactly one h and all the rest of them x's. And if you think back to your experience in multiplying out quadratics and cubics, that's what you see. When you do x plus h squared, you get x squared plus what? 2xh. When you do x plus h cubed, you get x cubed plus what? 3x squared h. So this agrees with what we've seen before. Now let's think ahead to what's going to happen here. This x to the m doesn't have an h in it, so we know it's going to have to cancel. And look, there's a negative x to the m coming later. That's great. This term is going to have an h in it. What's the next term going to look like? It's going to have something with an x to the m minus 2 now and an h squared. So this term is also going to have an h in it. In fact, all of the remaining terms are going to have h's in them. So we're going to be able to factor an h out of all of those terms and then cancel that h on the bottom. But when we factor an h out of this term, since it had an h squared, there's still going to be an h in this term, meaning that no matter what this coefficient is out here, when h goes to 0, this term's going to go away. So it doesn't matter what this coefficient is. We don't even need to figure it out. The next term is going to have an h cubed in it. When we factor an h out of it, it's going to have an h squared left in it. H is going to go to 0. That term's going to go away. So the coefficients on all of these terms don't even matter. I can tell you what some of them are. This one is m times m minus 1 over 2. These are the so-called binomial coefficients. But we're going to see that this didn't even matter. So then plus terms with h cubed, h to the fourth, all the way up to h to the m. And then finally, remember, we still have this minus x to the m term at the very end. And this is all over h. I hope you have a lot of space on your paper to write this. So just as happened when we did it with the quadratic and when you did it on the homework with the cubic, this term cancels that term. Every term left now has an h in it, which is exactly the situation we love to be in. So we factor an h out of those terms. Left from this term is mx to the m minus 1. And as we said, when we factor an h out of this term, we're still going to have an h in it, h to the first power. So even though I wrote what this coefficient is, it doesn't matter. This term is going to go away. So it's going to be this plus terms with what? This term that used to have an h squared now has an h. This term that used to have an h cubed now has an h squared. This term that used to have h to the fourth now has h cubed, dot, dot, dot. And finally, this term that used to have an h to the m now has h to the what? It should have h to the m minus 1. And this is all over h. So now we can cancel those h's, as we hope to do in every one of these problems, so that we're not in danger of dividing by 0 when we plug in 0 at the end. So now what do we get? We get the limit as h goes to 0 of this first term, mx to the m minus 1, plus all these terms. And again, I'm not just not writing the coefficients on them out of because I don't know what they are or because we can't figure them out. We could figure them out if we really wanted to. They're the binomial coefficients. You can look them up. They're well known and well understood. We don't need to know what they are, though, because all of these terms are going to go to what? 0, 0, 0, 0. All those terms vanish. And we're left with what? Just mx to the m minus 1. So there you go. There is our power rule. It says that the derivative of x to the m is mx to the m minus 1. Put that in a box. That's our first big exciting rule. So this will let us take the derivative of any power you want, x to the 1 million if you're really feeling like it. Now, we should admit one thing, though, which is that when I'm writing out this expression over here about writing this out m times and then doing this thing about multiplying, what are we really assuming about m without having said it? We were assuming that m was a positive integer. Because what if m had been pi? What would it mean to write this out pi times? I couldn't really do this. Or if m had been -3, I couldn't really do it in the same way. So this proof really only works for positive integer n. This is true for all real numbers m. This proof only works for positive integer m. We will prove it for all real numbers m next week. So our proof worked for positive integer m. But the rule holds for all real numbers m. And we'll prove that next week when we have this powerful tool called the chain rule. Let's use our rules now. So I've got some functions here, and I want to find their derivatives. So our first function is x to the 28th plus 6x. You might recognize those numbers, 28 and 6, from an earlier lesson. We'd like to take the derivative. So this actually is going to use 3 of our rules here, right? Because we have a sum. So the sum rule says if I know the derivative of this and I know the derivative of this, I put them together by adding their derivatives together. So do we know the derivative of x to the 28th? Sure. We just came up with the power rule. The power rule says the derivative of x to the 28th is 28 x to the 28 minus 1, or 27. That's using the power rule that we just developed. The constant multiple, or the sum rule says now I put a plus there. And now I've got 6x. We need 2 of our rules there. We can think about x as being x to what power? You can think about that as being x to the first power. And now I've got a constant multiple. So what does our constant multiple rule say we do with this constant? It says you keep it there. So it's 6 times whatever the derivative of x to the first is. But x to the first, we can use our power rule. It says the 1 comes down times x to the 1 minus 1, or 0. And then if we want to clean this up, we can say 28 x to the 27th. And this is just 6. And we shouldn't be surprised that that's just 6, because this is 6x alone. This function is a what? That's a linear function. Derivative means slope. What's the slope of the linear function 6x? It's just 6. Now you can imagine trying to do this using the limit definition. You're going to have x plus h to the 28th power. You'll multiply that all out. It'll have 29 terms. Luckily, a lot of them will cancel when h goes to 0, and you'll end up with this same answer. But I hope you'll agree that this shortcut is a much cleaner, faster way to getting to the answer. Let's move on to this function. Now, a lot of these terms look different than how we would like them for our x to the m rule, right? Because, for example, I don't have any rule yet for taking the derivatives of quotients or square roots. So before we take the derivative, we are not taking the derivative yet. We just need to use algebra to rewrite this in a way that allows us to apply our x to the m rule. So from the very first class, we know that square root of x can be rewritten as what? X to what power? We can rewrite that as x to the 1/2 power. And then this is minus 3 times 1 over x. But from another exponent rule from that first night, 1 over x is the same as x to what power? If you set x to the -1, you are correct. And then this is 4 times x to what power from the first night? X to the -5. And then 6 to the 7th. So now we've got things the way we like them. Now we can apply our 4 rules. So we've got x to the 1/2. Our power rule allows us to do that. It says we bring the 1/2 out front. And then the new exponent is what we get when we take the old exponent minus 1. So 1/2 minus 1, which is minus 1/2. Now here's something that we haven't seen yet. I've got a minus sign here. We have a sum rule. I didn't write out a difference rule. I didn't write out a rule for f of x minus g of x. Is that a problem? Did I forget? Should I have done it? Or can we combine two of our rules to get a rule for that, to get this? And the answer is we don't need a special rule for the difference. We can think about this is instead of subtracting 3 as adding what? We can think about it as adding -3. So this is really adding -3. We already have a sum rule to take care of the adding, and the -3, our constant multiple rule, takes care of that. So that's why if we have the sum rule and the constant multiple rule, we don't need a rule for differences. For subtraction, we put those two rules together and save ourselves. Mathematicians never want to have any more rules than they need. So here the constant multiple rule says the -3 stays, and then the power rule says the -1 comes down, and then this becomes x to the what? We want to subtract 1 from it, so -1 minus 1 is -2. And then we have another sum, so we do our sum rule. The constant multiple rule says what do we do with the 4? Keep it or let it go? We keep it. The power rule says the -5 comes down out front. And then we get x to the what? -4 or -6? -6. It's easy to get that wrong, but you're actually subtracting, so you want to have x to the -6. And then what about this? Should I bring the 7 down and make it 7 times 6 to the 6? No. 6 to the 7th is a what? It's a constant. It has no variables. You can put it into your calculator, ask your calculator what 6 to the 7th is. It's some big number, but it's a constant. And our very first rule from this week is that the derivative of any constant is always 0. And we don't require you to simplify your answers, so if you want to leave it like that, that's fine. I'm just going to clean this up a little bit. So this I can put the x to the 1/2 on the bottom as a square root. Here I can combine the two negatives into a positive over x squared. And here we can put this minus 20 over x to the 6th. Just makes it look a little bit nicer, but you don't need to do that. If you had written it like this, full credit. That's fine. Is that one okay? How about this one? This has also got a quotient, and we do not have any rule for taking derivatives of quotients. But unlike this one, I can't just instantly apply my exponent rules like that. Is there a way that I can rewrite this to let us use our power rule? And the answer is yes. We can first rewrite this as x to the 1/3 plus x squared over x squared. And then algebra always allows us to break up the tops of fractions, not the bottoms. So I can rewrite this fraction as this over this plus x squared over x squared. So x to the 1/3 over x squared plus x squared over x squared. And now we have one of our exponent rules from the very first night. I think it was called rule number 2, which says when I have something like this, what am I supposed to do with the exponents? We're supposed to subtract them. So 1/3 minus 2 is negative 5/3. And here, x squared over x squared is 1. So is that the answer? That is not the answer. We haven't done any calculus yet. All we've done is rewritten this using algebra. So now we can finally actually do the calculus and take the derivative of this using our rules. So the derivative of x to the negative 5/3, the power rule tells us how to handle that. It says the negative 5/3 comes out front, and we subtract 1 from the exponent, so we get x to the negative 8/3. And then since 1 is a constant, we've already shown that the derivative of every constant is always 0, because the graph of 1 is a horizontal line. So we can just write plus 0, but we don't really need to write anything there at all. So we've got 3 basic rules that apply to generic functions, and then the power rule. We can put them together to compute derivatives of infinitely many functions. And we've got to check your understanding on this now, so please go ahead and give that a try.